Hey, this is Horner, and this new unit is on alternating current. So we know that if you have a battery and you've got that battery running a flashlight, it has a constant potential difference. So that bulb that you see has a constant glow. The energy that we have or the electricity that we have in homes is a lot different. Rather than a constant potential difference, you get this sinusoidal variation. So it actually oscillates up and down and it goes from positive to negative. So if I was plotting potential versus time or EMF versus time, you would see this. And on a flashlight, you would see this. You would just see a straight line straight across. So that would be potential difference versus time. A light bulb in your home is on when the EMF is positive, but not on when it's negative. So it actually flickers on and off, and that flicker is pretty rapid. Happens about at a rate of 60 hertz. And so what you can do is you can take a slow motion video and actually see kind of what that looks like. So this is a slow motion video of that light bulb turning on and off. This is a compact fluorescent bulb, and so you can see it really well. If you try to do this with a normal bulb, it doesn't do it as well because um, that filament gets hot and it stays hot, so it continues to glow while it's hot. So that is the difference between the two. So I'm going to get rid of this and we will move on. So in the previous unit, we saw that a generator works by rotating a coil wire in magnetic field. That makes an EMF. And when it does, it creates that sinusoidal current and voltage that you saw. So this oscillation changes or basically charges to flow first in one direction and then the other direction a half cycle later. So we call this alternating current. If the EMF is constant and the current is always the same direction, then we call this direct current. So remember when we had a battery set up and it went to a resistor, maybe a light bulb, and back through, we always said it went from positive and then went to negative. If we have an AC source of electricity, and what it will do is it will go one way and then it will reverse direction. It will continue to do that over time, and that's because of the way the generator works that we saw earlier. Um, Alrighty, next slide. So here is the equation. This is for the instantaneous EMF of an AC voltage source. So this is whatever the EMF is at a particular time. And so it's equal to the original EMF times the cosine of 2 times pi times the frequency times that particular time. If you want to write this using period instead of frequency, we're just going to remember that period is equal to 1 over frequency. So that means frequency is equal to 1 over period. So here's the 1 over the period instead of the f. And that's what you'll see. So this is at a peak or a maximum EMF. T is the period of oscillation and F is equal to 1 over T. So here's our peak EMF, and then here is the negative, so maximum, or I guess you could say this is the bare minimum here. Period, remember, is just from one point on a wave to the same point on the next wave. So it could also be from here to here, that'd be wavelength, but that would also kind of tell you what the period is. So let's talk a little bit about curves. Let's talk a little bit about curves because I think if you just kind of look at a curve and you think about what it's doing, it's a lot easier to do a lot of this alternating current since we're dealing with sine, cosine, all kinds of different waves. So I'm going to put up just a couple of different things here. The first one is I'm going to start a wave here, and I'm going to move down, and I'm going to come back up. This one is what we call a positive cosine wave. And it's positive cosine because it starts above the 0 line, and that's a positive cosine wave. So then it starts down and comes back up. If I have a negative cosine wave, what it will do is it'll start down on the bottom, it'll move up, and it will come back down. So it's just the inverse of the other one. So how about sine? Let's go ahead and go through and talk about what sine is. If I have positive sine curve, it's going to start at the origin. It's going to move up first, back down, and then back up again. So that looks more like what I think what we're probably used to. A negative sine curve starts at the origin, moves down, comes up, and then comes back down. So these are the curves that we can kind of talk about. If we go back to the previous slide, then what we'll do is we can see that, here, let me go back to the previous slide. This is a positive cosine curve, and if you notice, that's what the EMF is doing. So we're starting here at this peak EMF. It is a positive cosine, comes down, comes back up. The question is, what about this 2 pi ft? So 2 pi is basically, anytime you think about a circle, if you start here and move all the way around a circle, we know that half of the circle is pi. So if I go from here over to here, that's pi. If I keep going around and go back to where I started, that's 2 pi. So that's where the 2 pi, we multiply that times the frequency. So 2 times pi times the frequency, that's equal to the angular frequency. So that's omega. So right here, this thing is the same thing as omega in rotational motion. And then we just multiply that times time. So hopefully that helps you kind of go back and remember some of the things that you probably did in wave motion or oscillatory motion. Let's talk a little bit about resistor circuits. In circuits where there's both current and voltage oscillating, we're going to use little I to represent the instantaneous current, and we're going to use lowercase v for instantaneous voltage. So be really careful that you recognize that these still mean current and voltage. It's just that it is instantaneous at any point in time. So why do we have to do that? Because remember, it's oscillating. So if it starts up here and moves down and comes back up, there are different times. So if we put little tick marks here representing different times, there at different times you're going to be at a different place in this cycle. You could be positive, you could be negative, you could be at zero. The potential difference across the resistor, so there's our resistor, is called the resistor voltage. So that's V with a little r down on the bottom. And it's related to current through the resistor by Ohm's law. So this is our equation, and you remember that equation when we did DC circuits. So it's V is equal to capital V is equal to capital I times R, and this one's just lowercase. And notice that we've put the R's here just to show that it's the potential difference across the resistor and the current across that resistor. So a little bit about resistor circuits. So here's a good picture of kind of what you'll see. The instantaneous current in the resistor is lowercase I subscript R, and the instantaneous resistor voltage is IR times R. So that would be the instantaneous voltage. So remember, this is oscillating back and forth. The potential decreases in the direction of the current. So if the current's going to the right, the potential goes down. And if this flipped the other way, we would have to put the plus on the right side, and we have to put the minus on the left. This is a good example of just a typical circuit. So what they'll do is, instead of a battery symbol, they're going to put this alternating voltage. So this voltage likes to switch back and forth. So that's an AC source. We can analyze this circuit with a resistor connected across an AC EMF. So this thing right here is your AC EMF. So that's your battery. If it was a battery, it would go in one direction, but it's not. It's alternating current, so it's a generator, so it's actually producing current going in both ways. The loop rule, the Kirchhoff's loop rule, says that the sum of all the potential around a path should be zero, and we do find that with this one too. Okay, so let's go ahead and talk about this a little bit more. We see that the resistor voltage is sinusoidal, so we know that it's cosine of 2 pi f, that's your angular frequency, times time. VR is the peak voltage, so when we think about the voltage going through that resistor, if we drew our bar graph again, I'm going to keep drawing it, then up here at the top, that would be our peak voltage, In a single resistor case, that peak voltage should be equal to the EMF. So the current through the resistor is just IR cosine of 2 pi ft. And that's just because we took the voltage of the resistor times a cosine of 2 pi ft over R. So IR here, now notice we have capital I because now we're talking about peak current. So this is instantaneous current, this would be peak current, and this has got to be peak voltage or EMF, and then R is just our resistance. Okay, so here is a good graph. This will show you kind of how the voltage and the current are related. The resistor's instantaneous current and voltage oscillate in what we call phase. So when my current is at a max, so here we're at a max, my voltage is also at a max. And then when they're both at a minimum, they're both here, and then they both cross the zero line at the same time. So the current is at a maximum and minimum values when the voltage is at maximum and minimum. So that's a really important part of this. We just want to make sure we see that voltage and current are always what we call in phase. So they follow the same path. AC power and resistors, the instant power can be written as, now here's instantaneous again, so we're going to use a lowercase p, so notice that's not a uppercase p, it's just a lowercase I squared r. Remember there were several equations for power. Power could be equal to IV. We know that power could be equal to I squared times r, and then power is also equal to V squared over r. So here we've chosen to use P is equal to I squared r, and we know that the I, instantaneous current, is really the overall current times cosine of 2 pi ft squared times r. So here we're going to do I squared r. We're going to take the I out. We're going to factor it out of this and just do I squared r times the cosine of 2 pi ft and make sure you see that it's squared. It does look very confusing, but it is really simple. So I is just the current in the circuit. The cosine of 2 pi ft gives us that curve, and r is just the resistance. So that should make it a little bit easier. I think everybody's thrown sometimes by all the cosines and then the 2 pi ft's. So don't let that confuse you. So the power oscillates twice during every cycle of EMF. So you'll notice that during one cycle of EMF, so this would be one cycle right here, we'll see that this actually goes through 2 cycles as it goes through. So that's another one of those things that you just have to learn to recognize on the graphs for alternating current. The current in a light bulb reverses direction 120 times per second, so the maximum, that power reaches a maximum twice per second. However, that bulb does glow steadily, so the average power is a little bit more useful whenever we're thinking about one of these light bulbs. So the average power is going to be equal to 1/2 of I squared r. So this is a little bit different. This is average power instead of just regular power. All we're doing is we're just halving this so that we get the average. And that's AC power and resistors. The other thing that you'll see here is in a DC circuit, we know power is equal to I squared R or V squared over R. And so we can use something called the root mean square current and the root mean square voltage to help us think about power. So you're going to see these letters RMS, that just means root mean square. And what we're going to do is we're going to take the overall current and divide it by the square root of 2. We can do the same thing with the potential. And if we use those root mean square values, we can write the average power dissipated in AC circuits as this. So as long as we work with RMS voltages and currents, the expressions for DC power will carry over to AC power. So we're really just trying to bridge the two, and by using this root mean square, we can do that pretty easily. This is a good example of using the RMS. And so this one says the resistance of and current of a toaster. So the hot wire inside a toaster dissipates about 580 watts when it's plugged into a 120 volt outlet. So they want to know 2 things. What is the wire's resistance? And then what are the RMS and peak currents that are going through that wire? So let's go ahead and solve the first part. So we're going to rearrange an equation we had earlier. So we know that power is equal to V squared over R. So here we're going to say R is equal to V RMS. Remember, we have to use RMS to get our power correct here. Squared all over power. So we know our RMS was 120 volts for our potential. Divide that by 580 watts, and you should get that 25 ohms of resistance. If I rearrange the other equation, the P is equal to I squared R, and rearrange it for the RMS current, I can plug in my values for both my power and for my current, and I find out that I have about 4.8 amps. So the peak, if I want the peak current, I'm going to use the RMS. I'm going to use this equation. So this is peak current. Peak current is equal to the square root of 2 times I times the current, and that gives us 6.8 amps. So this is our average, and then this is what it is at a peak. And that's the difference between the two, and that's kind of what happens when you have alternating current. You can't treat it as you could DC, where there's just one value for current. There's many values. We can get a average, and then we can also get a maximum, and that is 26.1. We do a quick check on our work. We can calculate the power for the rated voltage, so 4.8 amps times that 120 volts does give us 580 watts. So that agrees with the value in the problem, and yay, we're happy with our solution.